Okay, today I'm going to talk about continuity. And it's a very simple concept. All you have to understand is if the function has a break, it's not continuous. If it doesn't have any breaks in it, it's continuous. But what I want to do right now is make a mathematical explanation for that. Because in a math class, it's not good enough just to know it's not continuous. You have to be able to explain why mathematically you know it's not continuous. So let's take a look at this. So I'm looking at this function, f of x, and I see at x equals -4, it is clear that the function is not continuous at that point. Oops, let's put an n in there. Continuous. There we go. So it is not continuous at x equals -4. Now, how do I know that? Well, you could say look at the graph. Problem is sometimes, especially with your graphing calculator, it might actually show the point because I don't want to get too deep into it, but missing a point is infinitely small. So not all graphing calculators will even display that it's missing. So looking at the graph is not always a mathematical justification of whether something's there or not. So what I could do is use the formula if I have it, and most likely you will have it. So with the function, what I can say is, notice, when I plug -4 into the function, I don't get anything out. That value does not exist. This alone is enough information for me to make the argument that the function is not continuous at x equals -4 if it's not even there. So it doesn't even exist at -4. That's a good mathematical argument. However, as I move from left to right and I look at x equals 1, now when I look at the graph, it is clear that it is not continuous. But this is not enough mathematical justification. So let's try this. How about, does the function exist at x equals 1? And yes, it does. When I plug in +1, I get out 4. So the function exists there. I can't use that. However, take a look at the limit. So in this case, the limit as x approaches 1 of the function, this does not exist because it's approaching 4 from the left and it's approaching -2 from the right. So if the limit does not exist, that is enough of a mathematical argument to say that the function is not continuous at that x value, in this case, x value 1. Third case scenario. Let's take a look at x equals 6. I look at the graph and I can say, it's clearly not continuous by looking at the graph. However, that's not enough justification. So I'll go through the process again. Does the y value exist when I plug in 6? And the answer is yes, I do get a y value. So I can't say that it's not continuous because the function does not exist when x is 6. It does. When x is 6, the function is 2. So the point is there at 6. There is a point. How about the limit? That was all our second step. Well, problem is the limit does exist. Check that out. As I approach from the left of 6, I'm going to 5 on the function. As I approach from the right of 6, I'm going to 5 on the function. So there is a point on the function for that x value. There is a limit as x approaches 6 on the function. So neither one of those techniques were allowed to work this time. I have to come up with a new justification. And what we're talking about here is that this point is not located where this limit is. So f of 6 equals 2 is not the limit of the function as x approaches 6. So if these are not equal, I can say the function is not continuous. So now I'm going to formalize that a little bit more and basically say that the function is continuous at every point in its domain if every time x, for every single x value, the limit as x approaches any value a in the domain of the function is equal to the y value I would get by plugging that in. So both of those things all of that must exist. There must be an output at that x value, so there must be a y that corresponds to that a value, and that y value must be equal to the limit. So if this is true for every single value in the domain, I can say that f of x, that f of x is continuous on that domain. And that's for all a values in the domain. And that is your R lesson on continuity.